So this video is on Adjoint Operator. We have seen so far norm vector spaces, Banach spaces, and Hilbert spaces. So now we can speak about Adjoint Operator. So I remind you that the norm of U is positive or null is equivalent to the fact that oh, there is an error when I just start. It's very interesting. Okay, no, this is not equivalent. I mean, if the norm of U is equal to 0, not square, then the vector V is the vector null. Okay, it starts very well. So, but just forget this inequality. Okay, no problem. You can imagine. You can see it by yourself. So the norm of V plus W is always less than the sum of the norm of U and the norm of W. Okay, this is a basic triangular inequality now. Okay, so now let's consider a subspace. Okay, and the two vector V and W. W is a subset vector space. Okay, and we have the fact that alpha and beta are scalar from C or R. Alpha V plus beta W is included in the vector space. Okay, so norm vector space, we've seen it. We've spoken about the addition, scalar, multiplication. We defined the norm. We've seen in my previous video, two previous video, we've spoken about Banach spaces, and we've seen that a Cauchy sequence is equivalent to the convergent sequence. So when you can define the limit of a sequence, you use the Cauchy sequence. You demonstrate that it's a Cauchy sequence, and every Cauchy sequence in a Banach space is convergent. Okay, so we've already seen it in my previous video. About the Hilbert space, I remind you that we define the inner product such that the norm can be derived from this inner product by taking the square root of the inner product of a vector with itself. Okay, so this defines a norm. We also see and understand this double inclusion, which is very fundamental to understand the mathematical object we are speaking about and we are defining. An Hilbert space is a Banach space. Okay, so all the Banach space property are inherited by the Hilbert space, which means that Hilbert space is included in the Banach space, and every Banach space is obviously a norm vector space. So we start from the norm vector space. We add some properties. We define the Banach space. We add some properties, and we define an Hilbert space. Okay. So I'll give you some example of Hilbert spaces: Rn, Cn, L2n, as we define the sequence that converge for the norm 2, LP for the norm P. Okay, are Hilbert spaces. So now let's focus on the main subject of this video, of this mathematical lesson, which is the Adjoint operator. Okay, so functionally we define a linear map phi who goes from an Hilbert space, okay, and get from vector give us a scalar, so a complex. This is an Hilbert space, so a vector space. Okay, this is the scalar. So we consider also a functional, which is a bounded functional. So the bounded functional, there exists a constant k, okay, such that you have this inequality, which means that for whatever vector in our vector space, in our Hilbert space, okay, you have this constant k that you can measure the absolute value of phi applied to the vector v. Okay, I remember that phi is this application, okay, that take a vector and give us a scalar. That's why I take the module if we are in the complex, or the absolute value if we speak about the real of v. Phi of v is always less than k. Okay, k is a positive number, of course, multiplied by the norm of v. Okay, so this is the definition of a bounded operator. Okay, so now let's add some properties. Okay, there is representation theorem. Okay, so there exists a unique u, a unique vector, okay, that belongs to the Hilbert vector space, such that for whatever v you take in the vector space, The scalar product, the inner product of V with U, is defined as the application phi applied to V, okay, which means that phi of V is the inner product of V with U, okay, of these two vectors. So now let's consider a bounded linear operator, so which consider T that goes from H, okay, to H, we can consider it, and let W be a vector in our vector space, in our Hilbert space, okay? So the functional that we just defined, phi of V, that give us the inner product between T of V, okay, between the operator T applied to the vector V and the inner product between this and W. So the operator phi is linear and bounded, okay? Because phi is linear and bounded due to the Ries theorem, there exists a vector in H in the Hilbert space such that phi of V is the inner product of the vector W, yeah, and the operator T that is applied to V, okay? So this is also equal to the inner product between V and the T star of W. And we are just going to define this T star. T star it will be known as the adjoint of V. If there is a T star that verifies this equality about the two inner products, okay, then T star will be the adjoint, will be called the adjoint of the T operator. This is the way you define the adjoint operator. There is no other way to define the adjoint operator. So in this way, we just define a map that we can call T star. T star goes from H to H, okay, and take a vector in our vector space and give us the T stars of V, of W, okay. So T star goes from H, from key to K. So now let's enter in the major consideration of the adjoint operator, how it applies, what are its properties, okay. Just a parenthesis here, if you make some quantum mechanics stuff, you will on a daily basis using adjoint operator. So you really need to focus on the adjoint operator if you make quantum mechanics algebra. It's a very important concept. So the mapping T star that goes from H, the Hilbert space H, to H is linear and bounded. So let's prove it. Okay. So for the linearity, it's quite easy. Indeed, okay, T star of alpha V plus beta W is equal to alpha T star of V plus beta T star of W. Whatever vector in the vector space, V and W, you take, and whatever the scalar, the complex number, alpha and beta, okay? So let's demonstrate this by the definition. So let's apply this T star, okay? So let's do the inner product between the vector U and the operator T star applied to alpha V, to the linear combination of these two vectors with the prefactor alpha and beta to V and W. Okay, so this is equal to according to the definition of the T stars operator, okay, that I don't remember, you know, but this is the definition. You have to keep it in mind. You have to notice by T of the inner product of T of V applied to W is equal to the inner product of V and T star applied to W. This is the definition. So you have to keep it in mind. You have to use it. So now let's use this definition. Okay. So T star now comes T over U, and this is equal to the inner product between TU and alpha V plus beta W. Okay. So by using the definition of the squilinearity of the inner product that we just defined, we define it in my previous videos about it, okay? Videos on non-vector space, on Banach spaces, and Hilbert spaces. So this is nothing less than alpha complex conjugate, the complex conjugate of alpha multiplied by the inner product of TU and V. Okay, then I use the linearity of the inner product, okay? plus beta star, sorry, beta complex conjugate, the complex conjugate of beta, because beta is complex number, right? Multiply by the inner product of Tu and W, okay? So now let's use again the definition of T and T star. So the inner product Tu and V is equal to the inner product of U and T star U. Okay, right. So that's why when I pass from this line to this line, okay, I just change this inner product using the definition of T star. So T star, which is the adjoint operator, I remind you. And I make the same for the second equality. So the inner product of Tu and W, okay, is by using the T star, the adjoint operator of T, defined by the inner product of U and T star applied to W, okay? So we have these lines. Now it is quite down. We just have to merge the two inner product and and to use the linearity as a reverse engineering linearity, I mean. So by putting alpha complex conjugate inside on the right, you take the complex conjugate of the complex conjugate of alpha, which is alpha itself. That's why alpha comes inside the inner product as alpha, okay, and not alpha complex conjugate. This is on the right of the inner product scale. If it would be in the left, you would have alpha complex conjugate. So so this is equal to the inner product of U and alpha T star applied to U, plus I make the same thing for beta complex conjugate. I put it inside the inner product, you know, and I put it on the right because on the left it will be inside as a complex conjugate, but on the right it's the complex conjugate of the complex conjugate of beta, which is beta itself. Okay, so now it's very simple. We have the two inner product. We add the two inner products. I mean the inner product of U and alpha T star U, adding the inner product of U himself with beta T star and U is nothing less that by using the linearity 2 of the inner product, the inner product between U and alpha T star U and plus beta T star W. That's why that's what we wanted to demonstrate, right? That's the result we wanted to demonstrate. We just showed that hence T star is linear by lemma previous system. Okay. So now the definition of an operator bounded. So I remind you the definition of a bounded operator. Okay, so we define the norm. Okay, the norm of T star applied to V. This is a norm as the sup of the inner product of W and T star of V for all the W which have 1 as a norm. So this is the definition of the norm of the operator T star applied to a vector V, right? So we can also write it in this way by using the definition of the adjoint operator. So this is also equal, I mean the norm of T star applied to V is also equal to the sup for all the W that have norm 1 of the inner product of T applied to W and V. Okay, so T is linear and bounded. Okay, according to the Cauchy-Schwarz inequality, okay, we can measure, we can say that this number is inferior or equal, is inferior to the product of the norm of TW and the norm of V. So this is always less than the sup for W equal to 1 of the norm of TW multiplied by the norm of V, which is minor to the sup of the norm of T by the norm of W by the norm of V for the norm of V equal of, which is 1. But if we take norm of W equal to 1, we have that this is the norm of T by the norm of W by the norm of V. So at the end, the norm of T star V is inferior to the norm of T multiplied by the norm of V for whatever V you take in your Hilbert space. Okay. Here you can do without the star. Okay, so which is the norm of tw is less to the norm of t by the norm of v tv. Okay, so we have in some way the norm of t star is always less inferior to equal to the norm of t, because t is bounded. Okay, because t is bounded, we have that the norm of t by w is inferior to always the norm of t multiplied by the norm of w. Okay, now let's make an exercise on that stuff. Some exercise and some concept. Okay, so let's consider the operator, the following operator t, okay, that is going from LP of n and to LP of n. So we take a sequences that is convergent for the LP norm, okay, and give us on the based on these sequences another sequences that is convergent for the LP norm in here. So T take sequences, the sequences of xk for k from 1 to infinity, and gives us back the sequences of formed by xk plus 1 for k from 1 to infinity. So now we are going to show that T is linear and bounded. T has an adjoint. So let's take the two sequences, the sequences of xk for k from 1 to infinity, and the sequences of yk for k from 1 to infinity, that are two sequences that are convergent, okay, by the norm of L2. Okay, so now let's form the inner product, okay, on L2, the inner product for the L2 norm, okay, between t applied to the sequences of xk and the sequences of xk. So t applied to the sequences of xk give us the following sequences that I write it as a vector. We, for the first coordinate, we have xk for k equal to 1, so it's 1 x1 plus x1 plus 1 x2. Okay, so we have x1 plus x2. For the second coordinate, t applied to x2 will give us xk equal to, you just substitute the k you consider by the number you consider, k equal to x2 plus xk equal 2 plus 1, so it's 3. So it's x2 plus x3. So we understand the scheme here. So the third coordinate of this sequences is x3 plus x4, then x4 plus x5, etc., etc. Okay. So this is the inner product of this vector. This big vector we just explain how it is formed, and the sequences of its k. Okay. So the sequence is formed by y1, y2, y3, etc., etc. So when we make the inner product, okay, we make the first component with the complex conjugate of the associated component in the second vector. So it's x1 plus x2 multiplied by the complex conjugates of y1 plus x2 plus x3 multiplied by the complex conjugate of y2 plus x3 plus x4 multiplied by the complex conjugates of y3, etc., etc. Okay, so now what we do in this summation, we can see that we can make x1 in factor. Okay, x1 in factor of some terms, then we have x2 which will be in factor of y1 complex conjugate plus y2 complex conjugate, plus then you will have x3 which will be x3 will be, you make x3 will be factorized by here y2 complex conjugate and here y3 complex conjugate. So this summation is equal to this summation that you can see here. So you have x1 multiplied by y1 complex conjugate plus x2 y1 complex conjugate plus y2 complex conjugate, here I forgot, plus x3 complex conjugate y2 plus complex conjugate of y3, etc., etc. So if you see, we can form now this summation as the inner product of two vectors. The first one is the vector formed by x1, x2, x3, etc. And the second one is the vector formed by y1, y1 plus y2, y2 plus y3, etc., etc., etc. And this is nothing less than t12 of yk, which is the vector formed by y1, y1 plus y2, y2 plus y3, etc., etc., etc. Okay. So okay, I just make here before ending the exercise, just a summary of something that was clear to me at the time, and it was important to mention here. And then we will follow with the exercise. Just two lines to mention that. I could have mentioned it later, but it's not useless to do it right now. So obviously you have that t star star equal to t, which means that the adjoint operator of the adjoint operator of t is the operator itself. Okay, very important. If you apply twice the adjoint operator, you find the original operator. Okay, which was not so obvious at the end. And then of course you have the norm of t at the end is the norm of t, it's t star. Okay, and by using of course these properties of the adjoint operator, okay, you have that the inner product of v and t applied to w is the inner product of v and t t star to w, which is the inner product of t star v applied to w. Okay, so let take t from h to h, which is a linear unbounded operator. T is self-adjoint, means that its adjoint is itself. So t equal to t stars. T is unitary, means that t stars equal to t stars t, which is the identity. And for the special case where the Hilbert space is either Rn or Cn, when we speak about self-adjoint, we speak about symmetric. When we speak about unitary, we speak about orthogonal. Okay, so let's pursue. Let's go ahead by our exercise. So we consider so t, which is the operator that goes from LP of n to LP of n, with the properties t applied to the sequence of xk for k from 1 to infinity is the sequence of xk plus xk plus 1 for k from 1 to infinity. T linear bounded. T of xk is defined by the sequences, the following sequences. For the first component, x1 plus x2. For the second component, x2 plus x3. For the third component, x3 plus x4, etc., etc. And we see that t star applied to the sequences yk is nothing less than the vector, the sequences that have y1 for the first component, y1 plus y2 for the second, y2 plus y3 for the third, y3 plus y4 for the fourth, etc., etc. T is not here self-adjoint, so we don't have t equal to t star. And indeed, then, when we make t of t star of y1, y2, etc., we obtain this t of what? T of, so the result of t star of y1, 1 is x1, y1 plus y2, x2, y2 plus y3, y3 plus y4, etc., etc. So we apply then second time t to this vector, and what would we obtain? But we obtain y1 plus y2 plus y2, y1 plus y2 plus y2 plus y3, y2 plus y3 plus y3 plus y4, etc. So definition now of an inverse. Okay, then the inverse of t is the operators a, such as ts is equal to st is equal to the identity. And consider now as an exercise the following linear map: a, which go from cn to cn, a that applies to x vector is the following matrix. Okay, so you visualize it. So what is the adjoint of A in an Hilbert space? But the adjoint of A in the Hilbert space will be based by the complex conjugate. Okay, the complex conjugate of this matrix, and which is transpose. You see that here. I mean, A2, the coefficient A22, which is in the second line, first column, become the coefficient A12 complex conjugate, which is still in the second line, first column. So it's quite it acts as the transposition. So the complex, so the operator star, the adjoint, is nothing like that the transpose operator adding that the complex conjugates. We can sum up all these properties by this, that saying that when you transpose, this is the transpose operators, and the lines becomes colon and the colon become lines. Nothing more complex than that. So you change your line become colon and the colon become lines. This is the transposition. Then taking obviously the complex conjugate of a matrix means that you take the complex conjugate of all the element of the single of the complex conjugate of the single element of that matrix. Okay. So this is equal to the complex conjugate of A transpose. This is equal to the the transpose of the complex conjugate of A. So I will tell you that let B be a finite dimensional vector space, a collection of vector. So let's take the collection of vector vk for k from 1 to infinity in V. If there for each vector V there exists a unique sequence ck k from 1 to n, where ck is complex and the V is a linear combination of the vk unit vector, where v1 is the column vector with 1 in its first component and 0 in the other one, where u2 is not u2, it's v2 as 1 only its second component and 0 elsewhere, everywhere, and vn as 1 in its last component and 0 everywhere. So v is a linear combination, can be expressed of a linear combination of the vk vector with the vk vector from a basis for Cn. Okay, right, you can see it quite easily. Huh? No need to demonstrate it again. So that is, we will show now that for any u belonging to L1 of R, of n, there exists a unique coefficient ck. Ck is a complex number such that u can be expressed as a linear combination of the vk, such as u is the sum for k from 1 to infinity of ck vk. For any n natural number and any choice of ck, the norm of the difference between u and the sum for k from 1 to n, to major n of ck vk, is the difference of the norm of u1, u2, un, and c1, c2, cn as the difference of two vector of dimension n. Okay. So when you make the difference of two vector, you've got as a result a vector which is the different. I forgot the bar here of the norm space. You can add it and don't. Okay, so I forgot them. But it's so it's the vector composed by u1 minus c1, u2 minus c2, un minus cn. Okay, but this is also can be also right as the sum for k from 1 to n of the absolute value of uk minus ck plus the sum from k starting from n plus 1, right? Don't so from n plus 1 to infinity of the absolute value of uk. So if you want this, okay, double star, to go to 0, then you will see that ck equal to uk and some u that belongs to L1 of n, which is which where the sum for k from n plus 1 to infinity of the absolute value of uk goes to 0 when n is going to infinity. So this shows that u as a linear combination, sum for k from 1 to infinity of ck of vk with a unique choice of cu, thus the sequence of vk is a basis for L1 of n. Let the sequence of ck be the sequence that is chosen in the obvious way, then v is different from the sum from k from 1 to n of dk vk. Okay, now let's define a sequence. A sequence vk from K from 1 to infinity is a norm vector space in a norm vector space is called the basis for each V belonging to the vector space V if there exist a unique sequences, of course, unique sequences of CK from K from 1 to infinity such that V can be expressed like this. V can be expressed as an infinite linear combination. This is an infinite linear combination of the Vk throughout the coefficient Ck. So V is equal to the sum from 1 to infinity of Ck Vk. If you can find the sequence of Vk that define this, then you can say definitely that the sequence of Vk for K from 1 to infinity is a basis of your vector space. Okay. So where this of course means that the norm, the difference of the norm of the difference between V and the sum for K from 1 to up to n, major n of CKVK is going to 0 as n is going to infinity. Okay, these two definitions are equivalent. So I finish like this. I remember you that L1 of n is all the sequences, okay, all the xk where xk, it's not an n, xk belong to C, and the infinite sum k from 1 to infinity of the module of xk, or the absolute value of xk, is less than infinity, so it's bounded. Okay, so that there is an infinite series absolutely bounded. Okay, so we will show that Vk is a basis for N1, and I didn't do it. So anyway, you have more or less all the necessary concept for the adjoint operator. You can just learn by heart this one, which is the major. Then you will use it on a daily basis about adjoint operator. Okay, so that's all for this video.